Okay, today's video continues our discussion of projectile motion. And the type of problems that we've been doing so far involve projectile motion of objects that was fired horizontally from a height. So the type of problems that we're going to discuss today are what we call at an angle problems. So as the picture shows you, we're going to be looking at objects that are fired at an angle, so they're going to go up and come back down again. So there are some similarities in this to what we've done before, and there are some differences as well. So a motorcycle flying up in the air is going to have become a projectile, and it's going to have this motion of going up and coming back down again, fired up at an angle. So what are the factors that affect how far away the motorcycle is going to land? Well, we can talk about that in class, but you can already be thinking about it. And if you remember to remind me, I will tell you a motorcycle story when we are back in class. Okay, so how about this? If you're firing a projectile, what angle do you think gives the farthest range? What angle will make the projectile land the farthest away? Well, it turns out it is a 45-degree angle. A larger angle will send the projectile higher but not as far, and a lower angle will send it lower and also not as far. 45 degrees gives you the maximum range. Okay, so now we got some definitions. Hang time is the total time that a projectile is in the air for. And here's a projectile you might have been involved with, and you'd be concerned with how this is going to work out with the egg toss. You've got a projectile. And do you know that these egg tosses are now competitions, and they do it in colleges? Here's a college-level egg toss competition. And if you do not know your physics, and you do not know when the hang time is going to be finished up, you might just end up like this poor guy with some egg on you. He looks like it'll be okay. Clean that right up. Okay, so now, like we did for the horizontal projectiles, I'm going to tell you some things that are always true. So in the x direction, the acceleration is still 0. It always will be. And in the y direction, now we're talking about gravity. So on the way up, the acceleration will be negative 9.8 meters per second squared, and on the way down, it'll be positive 9.8 meters per second squared. We're always going to look at it on the way down. That's going to be our choice. Okay, in the horizontal direction, the speed is constant, just as it was for the other type of projectile problems. And another thing that we could say in the vertical direction, as gravity slows it down, in the y direction, at the high point, the speed will be 0 meters per second. And these things are going to help us solve the problems. They'll be true for every one of the problems. So as you're trying to solve these problems, you'll go back to this part in your notes, and it'll be very helpful in solving these new problems because they can be very challenging. Okay, so in the horizontal direction, t is the hang time, the total time in the air. And since we're going to be looking at the projectile in the vertical direction on the way down, we could say that the time to the high point is going to be half of the hang time. And this is going to be important for solving these problems as well. Okay, so you've got the basics. Let's see what we can do with this. The range is also going to be just like it was for the horizontal problems, that constant speed multiplied by the time, the hang time. Okay, so here is a diagram showing you what's going on, and the arrows are...
Monroe Township High School, please go into a shelter-in-place.
We're in a shelter-in-place now at the high school here. You heard it from Mr. Goodall, the principal. All right, the red arrows are representing the vertical or the y velocities, the upward velocities, and you can see that the arrows start out large, meaning they're going fast, and then they slow down, 0 at the high point, and then they change direction and pick up speed on the way back down. That's the red arrows. And the blue arrows have a steady length to them, and they're always pointing in the same direction horizontally. Okay, so the horizontal components don't change, and the vertical components do change. Well, why would that be true? Well, gravity. Gravity does not act in the horizontal direction, so there will be no acceleration in the horizontal direction. But in the vertical direction, it changes because of gravity. Okay, so let's try a problem here. Cannonball is fired, reaches a maximum height of 50 meters. There's the horizontal component, and we want to know the hang time And let's try this one out here. Well, first of all, we're going to identify the information as we do. And so the speed was in the horizontal direction 100 meters per second. I'm going to call that v. It never does change. In the vertical direction, I'm looking at it on the way down. And these are important things here. On the way down, the initial velocity is 0 meters per second because we're just looking at it, and I'm putting it in red, and you should make a note in your notes as well. We're always in the y direction going to look at it on the way down. So the initial velocity is 0, the acceleration is 9.8, and the distance, we were told, was 50 meters. So put a little light in the room here. So we can solve this problem because, well, this is a simplification here of d is equal to vit plus 1/2 at squared. Since vi is 0, that part cancels out. 1/2 of 9.8 is 4.9, and here is our setup for solving for the time. And to do this, we're going to divide both sides by 4.9, and then we're going to take the square root to undo the square. So it turns out that the time on the way down was 3.2 seconds. Now the question was, what was the hang time? Can you make a prediction for what the hang time is? Well, if on the way down is 3.2 seconds, then the hang time is 6.4 seconds. The time on the way down is half of the trip, so we double that to get the hang time. Okay, so the cannonball is in the air for 6.4 seconds, and that means 3.2 seconds on the way up and 3.2 seconds on the way down. So there you go. And we have some other questions about this type of problem, and here we go. At the end of the flight, what are the horizontal and vertical components of its velocity? Well, in the x direction, it's still 100 meters per second. It never does change. Let's take a look in the y direction, the vertical, the y direction. On the way down, vi is equal to 0, a is equal to 9.8, and the time is 3.2 seconds. So we have enough information here to find out what the final velocity is. And when we plug in our information, it turns out the final velocity is 31.4 meters per second. So there you go. That's how that works. And yes, and that's in the vertical direction. So, how about the at the end of the flight? Well, we already have the answers here, so they're posted up for you again. And I do want to point out that this is the same in the vertical direction as when it was launched. Now, the horizontal velocity is the same all the way through. The vertical is 31.4 at the beginning and 31.4 at the end. But in between it changes so that its high point is 0, and then it picks up speed again. But what we're pointing out here is that whatever the initial vertical speed was, that's also the final vertical speed. And they're in opposite directions, of course. Okay, so here's another question. What was the range of the cannonball? Well, that's in the x direction, the range is, right? So here we take the speed in the x direction, the 100 meters per second, multiply it by the time that it was traveling in the horizontal direction, which was the entire time, and there's how we get our 640 meters. These problems can be very complicated, so practice is going to be what helps you out. You may not get it the first time through. It may take a few times. But stick with it, and I think in the end it'll make sense. But yeah, it'll be complicated, a little more complicated than one-dimensional motion was. Although the equations are the same, but we have to apply them in a different way, and that can be challenging. All right, so here's another problem for you. I'm going to give you some information, ask for the maximum height, and there's the answer. And I'm also going to ask for the vertical component of the final velocity, and there's the answer for that one. And another question is the horizontal component of the velocity, and I'm going to give you the answer to that one. Now, I'd like you to give this one a try. Do your best you can on it, and when we get back to class, we'll go over it together. Well, that's all we have for this video. I hope it was helpful, and look forward to seeing you back in class. Wait a minute. Oh, we're all clear from the shelter in place, so that's good news too. See you back in class, and thanks for watching.
for the interruption. This is Dr. Hagan on